Okay, so where's the cameraman? All right, so as promised, I'm going to look at programming, value iteration, policy iteration for linear systems, and goodbye MDPs. I just mean goodbye this general section. So I'll explain what's next at the end of the lecture. So where were we? Let's see. We have this linear model. So remember we have this linear model. The only thing I'm assuming about n is its IID. So we do have a Markov chain, zero mean. Finite second moment, and I'm denoting its covariance by sigma. And so we solved the Lyapunov equation last time without any control. So the special case, the cost is quadratic, and there's no input, so this b is 0. So we solved Poisson's equation, and we found it was equivalent to what's called the Lyapunov equation. And what was that again? I don't care. We should stare at it again. So it's this is a linear equation in M that you have to solve in order to solve Poisson's equation. And if M is equal to something of M plus Q, it's going to be a contraction in some sense, this linear operator. And what you need is the eigenvalues of A, as you know, to be less than 1 for solution. That's sufficient at least. But it's the only case you care about because that means the system is stable. And we're not going to worry about systems that are unstable. Right? If it's not stable, we want to stabilize it, and that's the point of the input. So now here's where the algebra gets crazy. And I tortured those of you who registered the course with that homework assignment just to get a taste of the awful algebra. And you thank me for not, for not inflicting the algebra in class. I mean, getting your hands dirty is one thing, but having to watch somebody do lots of algebra is another. It's not useful. But how do you think about the average cost optimality equation? So how do you think about this without algebra? So we have quadratic cost. Where R is positive definite, Q is positive semi-definite, and if you don't know what that means, go look it up. But in particular, actually, we're going to need to factor Q. So whenever you say a matrix is positive semi-definite or positive definite, immediately you assume it's symmetric. Okay, that's part of the definition. And a positive definite, a positive semi-definite matrix can always be factorized in this way. And I just wanted to say this up front, we're going to need this later. But it means that if you look at X transpose QX, if Q is equal to C transpose C, you get that, right? we can put in a phony output and say that the cost on the state is just really the cost on y squared. So that's going to be useful. But the main thing is, what about the average cost optimality equation? We all know it's ugly. If a solution exists, then it's quadratic. Where m is going to be a function that blows up. And and based on that, we find that the optimal control is linear. And let's recall that. So once you know the value function, you know the optimal control. It's defined to be the minimizer. Right? So the u that minimizes this is a function of x, and that's the optimal policy. And we can go through and work this out. So PU is the conditional expectation. And the system, we need the system, we need to keep it. Let's keep this forever. So this is a conditional expectation. Given x equals x, u2 equals u, and noise is the noise. And so let's write that down. One more step. All right, so we did this before, and I'm not going to write it down again. So h is quadratic, and you get the ax plus nu times m. We did this last time. So when you stick this into a quadratic function, last time we saw, you get this times itself. You get a bunch of cross terms, but n has mean 0, so they disappear. And then you get something times like n squared, n's a vector. But you get 1/2 sigma squared m with the notation I used, where sigma squared m is equal to the trace of m times sigma. So this is just the same calculation we did last time. And it came from the fact that we end up with the n transpose m. So there you have it. Now, I want the left-hand side to equal to the right-hand side, and the algebra could drive you crazy. First of all, let's just get the policy. if you want to minimize a quadratic, you take the gradient with respect to u. And the halves are introduced just so I can get rid of a half. What do you get? You get the gradient of that with respect to u is just RU, because R is symmetric. It would be R plus R transpose, otherwise, over 2. You take the gradient, you'll get RU. And what happens if I take the gradient of this? I'll get this times m times b, I guess. Is the product rule. I have a u here and a u here. I take the gradient, I'll just get this times the gradient of this. Oh, wait a second, that's transposed. I want column vectors. Look at this mistake. Oh yeah, I flipped it around. I'm taking the derivative and not the gradient. So gradients are column vectors, derivatives are row vectors. if u was a scalar.
You have an in between.
Yeah, because I want this is I want n-dimensional column vectors.
There is an in between.
Yes, and I forgot my m as well. Thank you.
So the gradient of UTRU is RU?
Hold on. This is just taking derivatives of quadratics. So I don't know. Let's not get into it. So if it's that clear, you can see it confused me because there's a difference between derivatives and gradients and all that. But I'm just making sure that this is an n-dimensional vector. I need a column vector the same dimension as x. Okay. So this is in RD thing. I just don't want to spend a lot of time talking about the calculus. Okay, so that's what you get. That's supposed to be equal to 0, and there you have it. And I can monkey around a bit, subtract things around, add things around. What will I get? I'll get R plus B transpose blah blah blah. So if I take all the u terms to the left-hand side, all the x terms to the right-hand side, I get u equals minus kx, linear feedback. And what's k? Well, I just convert this. That's not too bad. I mean, you have to make sure you've got the, whether you're looking at row vectors or column vectors or whatever, you have to make sure you've got your gradients correct. Once you do that, you get the optimal control of state feedback really nicely. The thing you'd all be tempted to do now is, now that you know that u equals minus kx, you'd want to plug that into here and force this equality to hold. And that's when you'd end up with 100 pages of text. Okay. So how do you avoid the complication? Anyway, any questions? So it's just a calculus. I mean, double check. The gradient of this quadratic is this. You take the partial derivatives, that's what you'll get. Let's set up this. So I'll ask my question again. How do you get the average cost optimality equation? So we got the policy by taking derivatives. The best way actually to come up with the average cost optimality equation is complete the squares in this quadratic. So I've got this mixed quadratic, with I've got a pure quadratic in x, a pure quadratic in u, this mixed up thing, it's all funky. If you separate terms in the right way, you can make this easy. And it's less algebra. It's still not pretty. But what you can do is just recall that what this term in brackets is again. We have that. This whole thing can be written in a different way. It's equal to. You've got a pure quadratic term here. And if I took out the x terms here, I'd get a pure quadratic. And then I've got a constant term here. And I want to keep anything that depends on u. But I'm going to get the things that depend on u is going to be of this form. I'm going to stop here. Now, the first I claim is I can write this down without even doing any algebra. Now, given the fact that I got the calculus to say that the gradient is this with respect to u, that solving that equation is what I have to do to get the optimal u, then I know that the term is a function of u. I can write it in this way, plus some terms that don't depend on u. So a whole bunch of terms here that are constant or just functions of x and so forth. If I wanted to minimize with respect to u, I would get that. Okay? So I know this is true. I'll tell you what h is in a minute. That's algebra. But I claim that just you can, if I have a quadratic with this minimizer, it's going to be in this form. I can do it by algebra if you want. Now what about the quadratic terms? Well, of course, I'll get the x transpose x. And there's another pure quadratic here. There's the ax and m and ax. And what else? Anything else? Oh, yes. So to complete the squares, I had to introduce some junk. You notice that there's a blah times x times h plus blah times x. That's a pure quadratic we've never seen before. Get rid of it. So this term here is this times this times this, just subtracting out the pure quadratic. So that's what I mean by completing the squares. We add and subtract this term so we can factor this. And then playing around a bit, you can see what the h will be. It's some god-awful mess. It's a thing we just invert over. So you can You can complete the squares to make this much more transparent. Yep.
It should be X transpose, A transpose, and M transpose.
No, M is symmetric. Yeah, so M throughout is greater or equal to 0, and whenever you say a matrix is positive semi-definite, it means it's symmetric, and that's part of the definition. It's a convention. You know? And so this can all go now. Except for this. All right. So now you can see that if I minimize this over all U, that doesn't depend on U, none of that depends on U. I just have this. H is positive semi-definite, so this term is non-negative. So to minimize this, I make sure it's 0. Well, you make sure it's 0 by doing that. So we do have that. And when I minimize over all U, so now to solve the average cost optimality equation, it's just pattern recognition. Except I forgot a term, didn't I?
Sigma x.
Okay. So the first bit of pattern recognition is obviously that is equal to that. We knew that already. And then the matrix here, the M, is going to have to be made up by the Q here, this term here, and this awful mess here. Because when I minimize, all I do is I make sure this big long term here is 0. So that's the Riccati equation. At least what people in control call the Riccati equation is setting this M up to all the rest on top. So let me expand my goal slightly to give you an elegant result. So I don't just want a solution to this algebraic equation. I want a solution which is positive semi-definite, and I want this control input to be stabilizing. So a little bit stronger than the rest here. Well, if that's the case, and remember I said that Q could be factored. And I said, let's let y be equal to Cx. And the idea is I definitely don't want, I definitely want my cost to not be too small, for sure. And the idea is this, like x transpose qx what I want to know is that if the state blows up, I want to see it to the cost. That's the idea. Because what can happen is that I give C is 0. If Q is 0, there's not much hope. You know, I'm doing really great. I'll just set the control off equal to 0. You know? And so X could be blowing up, yet because Q is 0, I don't see it. So that's the that's the implication that's needed, that we can see if x is blowing up through the cost. And that's called detectability. And so let's give a formal definition. First it says that what's that one? If you have a d-dimensional system, you construct this observability matrix. You take this matrix C, and then look at CA and CA squared. Put in one more for you. All the way down to C times A to the d minus 1, where to get d as a dimensional state. That's called the observability matrix. And a detectability means that if you have a vector which is the null space of this observability matrix, if O times some state is equal to 0, that means C times X is a 0 vector, CAX is a 0 vector, and so forth. That implies that A to the T x0 goes to 0 as T goes to infinity. That's the definition of detectability. So anything that's not observable with this initial condition, without any noise, y would be 0. That's it. And if the output is 0, you want the state to decay to 0. It's called detectability. And that turns out to be good. So the theorem is that if you have these two conditions, there we have it. So stabilizing detectability implies a desired goal. I ran out of room. But that's our desired goal. So it implies that we do have a M which is positive semi-definite. It solves the Ercot equation. And the resulting feedback law we get is stabilizable. Because what ends up happening is you just ignore these states, all these states that are in the null space of observability matrix. You just let them die on their own. that's the idea. All right. So it just shows that this is stronger than you need. In practice, you can get away with much less. All right. So algorithms. My main goal was to I want you to know these results. I want you to know that's the Ergodic equation that every person taking stochastic control has to know. I would never expect you to memorize it, but it would be on a page of cheat sheets. And these basic, ideas of stabilizability and detectability, those are the fundamental concepts required to issue the solution. So, questions? So a lot of you haven't seen this before. It's okay, but this observability matrix is fundamental for all of life. So value iteration. Let's go back and think about what our theory would say about value iteration. So we know that if the n is quadratic, everything is before. Linear system, quadratic cost. If the n you prove by induction that if the n of x is equal to a quadratic plus a constant, you plug in, what do you think you'll get? Well, we've already solved this minimum, and you get a quadratic plus a constant. In fact, we know what the new constant will be. Because we know that we end up adding on this term that I called sigma squared mn. And that's the definition I had before. So just put an n there. That's my definition. Okay. So we've seen this. We saw this. We saw this before. And mn plus 1 satisfies the Riccati recursion. I hate to do it, but let me write it down. This is where I feel like I'm wasting ink, but I feel like I need to. So what you get is before we had a Riccati equation we had to solve, now we get a Riccati recursion. That new m is a function of the old m. Well, that function looks identical to what we had before. So hn is defined exactly as h was defined before. What was that? It was r plus 1. Okay, and you get that, we did it, it's plug it and see. So we did that. Now, what does our theory say? Well, remember that we had if the first Lyapunov function was V0 is a Lyapunov function with some policy. So the notation we looked at before, if we take the nth policy, applied to the nth Lyapunov function, it's less than the Lyapunov function. It's a Poisson inequality. Okay? And then eta bar n was equal to the sup over x of Vn of x minus Vn plus 1 of x. That was the definition. So go back and look at your notes. And by V0 being a Lyapunov function with some policy, just look at the theorem. It says this equation holds for some policy. Now these guys are quadratic, you know. And wait a second, have I got this right? This is bigger than this. Oh no, I've got these backwards. Don't I? Sorry. It's Vn plus 1 minus Vn. These are quadratics, right? Quadratic plus a constant. Well, this is positive semi-definite. So what's the solution to this quadratic equation? What's its maximum? Well, if you've got a quadratic function and you want to maximize it, you get infinity. So there's infinity? Not necessarily. Some quadratics go like this. Now the only way in the world this is going to be finite is if this matrix here is negative definite. You know. So we know it's finite. These guys are finite. We proved that eta bar n plus 1 is less than equal to eta bar n, less than equal to eta bar n minus 1, dot, dot, dot. Sorry about my etas. We proved these are finite. So the only way this can be finite is that this matrix has eigenvalues which are all less than equal to 0. Which means that mn plus 1 is less than equal to mn. And in fact, if that's the case, if this matrix is positive, its negative is positive semi-definite, the supreme is attained at x equals 0. In fact, it's not just finite; it's equal to 1/2 sigma squared. So in this case, we get, it's not actually an inequality, it's a whole. Is that right?
Shouldn't
No, it's an inequality. It's one inequality. Yep.
Shouldn't that be like the kn instead of 1/2 sigma squared mn? Because we didn't show that kn plus 1 is equal to 1/2 sigma squared mn plus 1.
No, we did it here, but I'm just talking about this. If all this shouldn't be, so this is a lowercase k. I'm just saying, first of all, let's just backtrack here. If the nth value function is pure quadratic plus a constant, then we've seen that when you go through and you solve this, you get a constant term. And the constant term is nothing but this quadratic.
Yeah.
That's it. So when I subtract this from this, I just get the difference of that and that. So that means right. The K is in the background. There is a K hiding. So that's that. And so it is an inequality because, but the inequality is sweet because what you're finding is that what this inequality really becomes is Pn, Vn is less than or equal to Vn minus Cn. Hold on. Right down. Well, it's just giving us an upper bound in the inequality. All right, so because with so this is just an upper bound of the inequality. That's all I'll say. Because we have to solve Poisson's equation to get the actual average cost. And these are decreasing. Yep.
Is there 1 and 2 before that term?
Say that again?
Like v n plus 1 minus vn is equal to like 1 and 2.
No, just subtracting this from this. You know? And this is a linear function of n. This minus this is equal to that.
What about the 1?
I'm taking this minus this. And those and those cancel, and just left with that.
No, I'm talking about the 1 and 2 before the.
No, I'm just taking
The
this.
parameter there.
Where?
Half.
You guys
That
got
half.
one half.
that
Oh, I left
half.
that